Hi everyone, my name is Yebo Feng. I'm a second-year PhD student from the University of Oregon. Today I'm going to present our paper, Application Layer DDoS Defense with Reinforcement Learning. Two co-authors are Li and Thanh Nguyen. Application Layer DDoS attack, or L7 DDoS attack, is different from traditional DDoS attack. It represents a type of malicious behaviors that intended to target the application layer in the network model. Usually, the traditional DDoS targets at the lower layers, for example, overwhelm the link, the router, or switch. However, L7 DDoS, they directly use L7 messages to attack the application zone. So the mechanism of L7 DDoS attacks are different from the traditional DDoS attack. And we categorize L7 DDoS attacks into three types. For example, request flooding attack. Those attacks will overwhelm the victim system by sending a large amount of application layer requests at a very high rate from different IP addresses. For example, HTTP flood, SMTP flood, SIP coin control flood. They are also leveraged attack. Those attacks leverage the flaws of the victim system to amplify the threat. For example, low and slow attack, AIP-based attacks. They are also lethal attacks. This type of attack is more intelligent. The attacker will first scan the victim system to pinpoint the performance bottleneck. For example, the I/O system, the memory space, or the database server. Then the attacker will send a large amount of related requests to overwhelm those specific bottlenecks. Nowadays, L7 DDoS is on the rise, which occupied around 38% of the total DDoS attack during 2018. Compared with the traditional DDoS attacks, L7 DDoS is harder to detect and mitigate because the traffic patterns generated from L7 DDoS are usually legitimate in the network and transport layers. In addition, there are different mitigation methods for L7 DDoS, and each of those methods have different efficacy towards different types of attacks. So it is very difficult for us to choose a suitable mitigation methods for different attacks. The design philosophy of the existing method is we first use some information extraction, then use some attack detection and classification methods to label the traffic messages. And in the end, the mitigation module will perform the mitigation based on those labels. So the detection and the classification module are separated from the mitigation modules. What's the problem of this mechanism? First of all, the application messages with malicious and legitimate intentions are usually very similar to each other, and sometimes they are even identical. It is very hard to perform very accurate classifications on those type of messages. Secondly, different attacks have different suitable mitigation methods. We cannot just isolate the detection and mitigation modules. So here is our design idea. Can we just skip the detection classification steps and directly generate the mitigation actions? Our goal is to mitigate as many threatening requests as possible during a very severe attack. This might sacrifice a little bit false positive rate, but the system is under attack, it doesn't care. In addition, we want to minimize the collateral damage during a system's routine operation. This might sacrifice a little bit true positive rates. In the end, we want to ensure the efficiency during the defense procedure. Thus, we built a reinforcement learning-based L7 DDoS defense solution to solve this problem. Here is the operational model of the proposed method. Reinforcement learning is an area of machine learning which focuses on how the agent should take actions in an environment to maximize the cumulative rewards. The environment is typically stated in the form of a Markov decision process. So the defense agent will observe the state of the environment, then generate an action to the victim server. And the environment will take the action and give a reward and the next state to the agent. Now let me introduce some key components in the system. First of all, state. Each state is represented by a state vector S. S has 12 dimensions, and each dimension of S is a value that represents a feature. 8 of the dimensions are request-related state S prime, such as a client's average behavior interval, request consumption, request size. S prime basically tells the agent the client's behavior model to figure out how likely this client would be a malicious client. Also, we have server-related state S double prime, such as CPU utilization, memory utilization, and link utilization. S double prime basically tells the agent how dangerous the current environment is, and to help the system figure out what's the redundancy of the current victim and how likely it is under an attack. We want our system to calculate all those features in real time. However, some of the features are very expensive to calculate. For example, the number of similar requests. Since it is application layer message, traditionally we need to conduct a very complicated pattern matching on the message streams, then figure out how many message streams are similar to each other. To accelerate this procedure, we utilize the locality sensitive hash. We use this hash function to convert each application layer messages into a hash value. Unlike other hash functions that will generate random numbers out of similar strings, locality sensitive hash will generate similar results out of similar input streams. Then we just define a threshold to figure out how many results are close to each other, and finally output the number as a number of similar requests. Now let me introduce the action module. We designed 6 types of actions to tackle the client's requests. They are scheduling actions, which means the system will properly process your application requests, but maybe the system will do that immediately, maybe the system will do that later. There are also mitigation actions, which means the system will drop your application requests. The system can choose to drop the current request, or drop all the similar requests, or even drop all the requests from the IP addresses. These actions can be further classified as single targeted actions and multiple targeted actions. We want to design the reward function in a way that encourages the agent to generate multiple targeted actions rather than single targeted actions, because it is more efficient. It not only affects the current requests but also applies to some other requests in the future. The system can deploy those actions in the router so that the system don't need to spend extra computing power to process those application layer messages. Now let's move to the reward function. We designed a set of reward function to satisfy the system design. Here is the reward function when the system consumption is very low, which means the system is still in a very safe zone. For single targeted actions, the agent will get more penalty when mitigating false positive samples. Here we define false positive samples as a message as a legitimate message. However, the agent dropped or mitigated that action. In this scenario, which means the agent is encouraged to minimize the collateral damage in this situation, even though the agent failed to mitigate some malicious messages, it is still okay. The penalty is only -1. For multiple targeted actions, the reward function is the sum of all the effective messages rewards and times by eta. Eta is a value larger than 1. The design is to encourage the agent to take multiple targeted actions rather than single targeted actions. So when the system is under very severe attack, we want the agent to mitigate as many threatening messages as possible. We design another reward function to achieve this. The reward function is as follows. This reward function ensures the higher the system consumption is, the more the agent cares about the true positive rates of mitigation, and the less the agent cares about the false positive rates. We also designed the hazard index G. It is the input parameter that determines how eager the victim system wants the attack to be mitigated. The higher the hazard index G is, the more rewards the agent will get for mitigating true positive samples, and the less penalty it will get for mitigating false positive samples. Here is a curve of the reward function when the system is under very severe DDoS attacks. The y-axis is the system load, which means the system consumption. As you can see in the figures, with the increase of the system load, the penalty for mitigating false positive samples will decrease, but the reward for mitigating true positive samples will increase. Also, the penalty for missing an attack would be more. You can also clearly see how the hazard index G would affect the rewards that an agent could get in different scenarios. For multiple targeted actions in this scenario, the reward function is also the sum of all the affected application messages rewards and times by eta. The detailed reward function is as follows. Here we also define an eta as a reward multiplies for adjustments of the reward function, which is a value larger than 1. Because we also want to encourage the agent to take as many multiple targeted actions as possible. The agent will get more rewards if it did correct under this scenario. The agent will also get more penalties if it didn't did correct actions. Now let's move to the evaluation of this work. First of all, we evaluated the mitigation accuracies. Here we set the transition parameter as 0.75, which means if the system load is lower than 75%, the agent would use conservative strategies to mitigate the attacks. If the system load is higher than 75%, the agent will switch to a more aggressive mitigation policy. From the figure, we can clearly see when the system load is under the transition parameter, the false positive is almost equal to 0. Although the agent didn't successfully mitigate many true positives, but the server still have enough redundancy. The goal of the agent now is to minimize the collateral damage, even if it will sacrifice a little bit true positive rates. When the system load is higher than 75%, the accuracy and the true positive rates increase significantly. However, the false positive rate also increased a little bit, because the target of the agent now is to mitigate as many threatening requests as possible, even sacrificing a little bit false positive rates. We then evaluated the mitigation efficacy of our approach. If we assume that a server is considered to be proper functioning when the denial rate of legitimate requests is lower than 20%, the capability of the simulated server without protection is 140 requests per second. If the number of malicious requests goes higher than this value, then the server is DDoSed. With our reinforcement learning approach, the denial rate of legitimate requests goes only higher than 20% after the number of requests hitting 440 per second, which is 3.15 times the capability of the unprotected server. We also evaluated the service delay of our methodology. Because the reinforcement learning agent need to take some time to decode and process application layer messages before the server replying to the client. So theoretically, the agent will cause some delays to the server. Here, the delay is defined as a time duration from sending out a request to receiving the whole reply. Since we are testing with an HTTP server, the delay is calculated as the time the browser sending out the HTTP GET request to the whole page getting loaded. The delay without any defense approaches implemented is around 0.25 seconds. With our approach implemented, the average delay time still remains under 0.5 seconds when the system workload is less or equal to 90%. When the system is under DDoS attack, the delay goes to around 1 second. But good news is the server is still properly working. Without any defense solutions implemented, the server would be crashed in this case. Now, finally, let's move to the conclusion of this paper. This project proposed the first reinforcement learning-based L7 DDoS defense approach. It continuously monitors and analyzes a variety of metrics that are related to the server's load, the dynamic behaviors of the clients, and the network load of the victim to detect and mitigate L7 DDoS attacks. This approach employs a new multi-objective reward function that can minimize the false positive rate to avoid collateral damage when the system load is still very low, and it also maximizes the true positive rate to prevent the system from crashing when the victim system load is high enough. So this approach performs the mitigation with acceptable delays. It also detects more than 98% of the L7 DDoS traffic flows as a peak system load, and it can mitigate most of them. In the end, thanks for listening to this presentation, and we also would like to thank Dirk from the University of Oregon for proofreading this paper and provide suggestions on this work. So feel free to ask any questions if you have.